Hello, in this video, I'm going to introduce different asymptotic notations to represent time complexities of given programs. I'm going to start with the mathematical definitions of asymptotic notations, and then after that, in the following slides, I'm going to give you some examples and illustrate these notation using different examples. So sometimes we call asymptotic notations big O notations because the most commonly used asymptotic notation is the big O notation that you see here. The definition is, it seems to be very complex. Let me first show you the definition, the mathematical definition. It says g of n is big O of f of n if and only if there is some positive c and some positive number n0 such that for every n greater than n0, g of n is less than or equal to c times f of n. That's the definition. If you have taken some calculus, you may know this is very similar to the definition of a limit. So I can say the limit of g over f should be either a constant like c, or it should be 0. If that's the case, we can say g is equal to or big O of f, right? And let me give you some examples. You can say n is equal to big O of n. You can say n squared is equal to big O of n squared over 5. You can say n cube is equal to big O of 3 times n cube. And if you want to know the intuitive meaning of big O, all you can think of is that when we say g is big O of f of n, it means that the growth rate of function g of n is less than or equal to the growth rate of function f of n. So the big O is similar to the less than or equal operator that we use between two numbers. But instead of comparing the values of the two functions, it compares their growth rate. Growth rate means which one grows faster, right? And as you see, a constant value multiplied by n cube is not going to have any impact on the growth rate of n cube, because n cube grows in a similar fashion regardless of what its coefficient is. Similar to like this example, n squared is big O of n squared over 5, because n squared over 5, they both have the same n square term, but they have like different coefficients. The coefficients do not affect the growth rate of functions, right? One more example, maybe I can say n is big O of n squared, but I cannot say n squared is big O of n, because the growth rate of n squared is bigger than or is more than the growth rate of n. But the other way around is so n squared cannot be order of n, but n is equal to big O of n squared. That means the growth rate of n is less than or equal, in this case it's less than the growth rate of n squared, right? And I can show you like many other examples of this, but that's good enough for the start. You can always think of big O as a less than or equal operator between the growth rate of two functions. There's one more detail about this definition, and that's basically the properties of f and g. We're going to assume that f and g are two increasing functions with non-negative domain and target, which is um, which is a very good assumption, since we are using asymptotic notations to compare the time complexities of two algorithms. Let's say f and g are representing the time complexities of two different programs with an input size equal to n. Right? So obviously the size of input cannot be negative, so the domain is non-negative, and also the target cannot be negative because f and g represent the time. The time means how many seconds or how many instructions or how many clock cycles it takes for the computer to run a program, right? That's what time complexity means, right? Even you can consider f and g as functions representing the space complexity. Space complexity means how many bytes of memory do programs need to run, right? So if f of n represents the space complexity of a program, that means assuming the input size is 100, the amount of space the program needs is f of 100. Right? So f of n would be basically the space complexity or the amount of space that the program needs for an input size equal to n. Right? So I just wanted to tell you the relationship between this f and g and the actual program's time and space complexity. After after introducing this notation, which is the most commonly used asymptotic notation, let's briefly go over some other notations that are less common, but they are important to understand. One of them is capital omega. G of n is capital omega of f of n. If and only if f is equal to big O of g of n. So omega is just the opposite of big O. So that means if g is big omega of f of n, that means f is big O of g of n, right? And if you want to use the same limit definition, you can say g is omega of f if and only if the limit of f over g is either a constant or it's 0. And intuitively, you can say big omega means greater than or equal in terms of growth rates. So if g of n is big omega of f of n, it means that g grows with the same rate or even faster than f of n. Another notation is theta. We can say g of n is theta of f of n. And theta basically intuitively means they have the same growth rate, right? So g of n is theta of f of n if g of n is big O of f of n, and also f of n is big O of g of n, right? So that means they both have the same growth rate. For example, I can say, let's use another color, let's say blue color. I can say n cube is theta of 3n cube because they grow in the same rate. The growth rates are the same. And also I can say n squared and n squared over 5 are a big theta of each other. You can say n squared is big theta of n squared over theta over 5. However, I cannot say n is big theta of n squared. That's not true because n grows slower than n squared. Or I cannot say n squared is big theta of n, right? But what can I say about n squared and n? I can either say n is equal to big O of n squared, or I can say n squared is equal to big omega of n. What I cannot do is, what I cannot say is n and n squared are big theta of each other. That's not possible. because theta means growing with the same rate. Then I have two more notations. One is small o, one is a small omega. Small o means like one function is growing with a slower rate compared to the other function. So when g is big O of f of n, it means that g of n grows slower compared to f, right? So it's kind of similar to the big O, but instead of less than or equal, it's kind of similar to less than. So if big O is similar to less than or equal, small o is similar to less than, right? If big omega is similar to the greater than or equal, small omega is similar to greater than, right? Or, in this analogy, you can say theta is just like an equal sign, right? Let me show you the definition, the actual mathematical definition of small o. It's a bit too complicated, but again, if you are familiar with some limit definitions in calculus, this is not too complicated, right? So here's the definition. It says g of n is lowercase o of f of n if and only if there is some positive c such that for every n0 and for every n greater than n0, g of n is less than c times f of n. The big difference between this definition and a big O definition is that here I have a for every, here I have there exists. Long story short, you can create an equivalent definition for the lowercase o notation using the limit operation. You can say g of n is lowercase o of f of n if the limit of g over f is equal to 0 when n goes to infinity. So g over n should converge to 0. And if I want to help you make more sense out of these limit definitions, I can say big O notation or asymptotic notation in general only cares about big values of n. That's why we care about the limit when n goes to infinity. And there's an important reason behind this. Why do we use asymptotic notation when we want to compare like two algorithms' time complexities? The reason is we don't care about the small input sizes. When you have like two different algorithms, you want to find out which one works better or works faster. We don't want to we are not interested in comparing them for small input sizes, because for small input sizes the time of an algorithm doesn't really matter, because even if it's if an algorithm is a very inefficient algorithm, for small input sizes they don't have any problem. But when the input size grows, when n goes to infinity, which algorithm performs better is the critical question. And to answer that critical question, we use asymptotic notation, right? And that was so the last notation is a small omega. A small omega is the opposite of small o. I can simply say g of n is a small omega of f of n if and only if f of n is a small o of g of n. And that basically means the limit of f over g when n goes to infinity should be 0. As you see, for a small o I had g over f, for a small omega I have f over g. Now let's take a look at some of the functions that appear very frequently as growth rates of different algorithms and computer programs. These growth rates or these functions have are so common that they have specific names. So the first one is a constant function. That's called the constant growth rate. Let's say you write a program that always takes 10 instructions to be executed regardless of what the input is, right? That we call it constant, right? As an example, like when you're trying to read, let's say, the first element of an array, you always have to spend a constant time regardless of how big the array is, right? If the array size is 10, it takes you the same amount of time to get the first element than when the array size is a billion, right? The next one is the log n. That's going to give you the logarithmic growth rate, and log n. It doesn't matter what the base of the log is. Normally, when we say log n, the base is 2. In computer science, all the bases are 2. We don't care about the natural logarithm. We don't care about the base equal to Euler number or base 10, none of that. When we say log, the hidden assumption is the base is 2, right? And a very famous example of a program or a algorithm that results in a growth rate equal to log n is the binary search. Binary search means when you have a sorted list of elements and you're looking for a given target, instead of going over the whole array from beginning to end in a linear fashion, you can search for it in a using a binary search algorithm. The algorithm is very simple. You start from the middle, you compare the target with the middle element. If it's equal to the target, you're done. But if the target is less than the middle element, because your array is sorted, you have to only continue the search for the first half. And if the target is greater than the middle element, then you're going to focus only on the right half of the array and you can ignore the left half, right? Because in each comparison, you're going to have the search space. You're going to end up with a logarithmic growth rate, and the number of comparisons that you need to do before you find a given element in a sorted list using binary search is in the order of log n, right? I can prove why it's log n, but it's not really that important. Also, log s square is another common growth rate. You can also find algorithms that take, log cube or log to the power of 4, 5, those type of growth rate, but they're similar to logarithmic growth rates. Then after logarithmic growth rates, we have linear growth rates. Like, for example, the cost of a linear search. Let's say you don't have a sorted array and you're looking for given a certain value, right? You have no choice but to look at each and every single element in that array. If the array size is n, then the number of comparisons would be n. That's called the linear growth rate, right? That's going to be a linear search is an algorithm with a linear growth rate. Then we have quasi-linear, which is n log n. The functions that I'm going to read, I'm reading for you in this table are basically sorted based on their growth rate. The more I go forward, the faster they grow as a function of n. So n log n, which is called quasi-linear, is another typical growth rate. The best sorting algorithm based on comparison is quasi-linear, and there are many famous algorithms that take n log n to be executed. Here in this plot, you can see the running time as a versus input size. The x-axis is the input size, and the y-axis is the running time. This dashed curve is n log n. As you see, it's very similar to the linear, but it's a little bit faster growing than linear. If I want to draw n here, it looks like this. Okay, so as you see, n and n log n are very similar. N log n is a little bit faster growing, and then we have n square, n cube, and finally to the power of n. N squared is called quadratic. There are many algorithms that take n squared, like bubble sort. N cube is another type of like cubic growth rates are another class of algorithms that take n to the power of 3 to be executed, where n is the input size. And you can see the plots of quadratic and cubic. This one is quadratic, this one is cubic. As you see, the difference is too much, right? But both cubic and quadratic are called polynomial growth rate. They're still much slower growing compared to the exponential growth rate. Exponential growth rate, which is 2 to the power of n, or 3 to the power of n, or 10 to the power of n, are like super slow algorithms. The time complexity is growing super fast, right? Therefore, because the time complexity is growing super fast, it is almost impractical to solve or to run an algorithm with exponential time complexity for a big input size. Okay, and normally, you know, when you're doing some brute force, should I call it brute force? Maybe, yeah. If you're doing some brute force algorithm, just search for, let's say, a subset in a set, because the number of subsets is going to be 2 to the power of n. You're going to end up at an exponentially an exponential time complexity for your algorithm, and that makes your algorithm impractical. Your algorithm cannot be executed on even a supercomputer for a big value of n, right? So this is basically the list of most commonly used growth rates for you know, representing time complexity and space complexity of different programs and algorithms. All right, so let's see an example of a Java method. It's a public static method, and let's see if we can find its running time or time complexity using the big O notation. What I'm going to assume is the time complexity of this Java method is equal to f of n. What does that mean? That means assuming that I'm passing integer n as the input of this, as the only input parameter of this method, it takes a computer or a CPU f of n different instructions to successfully execute this method, right? So from the time that the method is called until the time it returns, if you count how many instructions CPU has to run, or the program has to execute, that count would be equal to f of n, right? That's called the time complexity. Now the question is, time complexity is big O of which of the functions that I showed you in the previous slide? Is it linear? Is it quasi-linear? Is it logarithmic? Is it the square of a is it like log of n squared? Is it n squared n cube to the power of n? What is it? In order to answer that, I'm gonna meticulously count how many instructions we need to execute in order to run this method, right? In order to process this method. And when I'm counting the number of instructions, I'm going to make some assumptions. I'm going to assume that an equal sign, which is basically an assignment operator, is one instruction. Any comparison like less than or equal is one instruction. Plus plus is two instruction because it's a plus one and then an assignment. Multiplication is one instruction. Plus equal is two instruction because you have to first add and then assign. Returning is one instruction. Jumping from the end of the for loop to the beginning of the for loop is another instruction. And declarations are don't need to be counted as instructions because declarations are going to be used only by compilers. They're not going to be used in the runtime. So in order to calculate f of n in a very exact fashion, I'm going to get the exact value of f of n based on the assumptions that I said. I have to go line by line and do the calculations that way. This one doesn't have any instruction in it. This one has only one instruction, the partial sum equals 0. In this for loop, I have one instruction for the assignment of I to 1. That happens only once for the whole for loop. That's called the initialization step of the for loop. And then this for loop, which iterates for n times, needs the following instructions in every iteration. We have a plus plus, which is basically two different instructions, plus the comparison less than or equal, that's one instruction, plus we have 1 and 2 multiplications, plus we have a plus equal, this is two instructions, and that's it, right? So this whole for loop will take us how much time? This is 2 plus 2 plus 2 is 6, 6 plus 1 is 7n, right? I will say 7n plus 2. Why do I add two more instructions? One of them is obvious because I have to initialize I to 1 at the beginning, right? And the second unit that I added to the 7n is because in the very last iteration, when I set I equal to n and I run the body of the for loop once, I will increase I by 1 again, and then I will compare I with n again. When I is n plus 1 and the comparison of n plus 1 less than or equal to n results in false boolean. And so that's the very last instruction of the for loop. So it's going to be 7n plus 2 in total. And this last line also takes 1, right? So if you add everything together, we have the partial sum, that's one instruction, plus this for loop, which is 7n plus 2, plus the last line, which is partial sum, and that's going to be one instruction. What I did not count was jumping from the end of the for loop to the beginning of the for loop. That needs another n instructions because at the end of the for loop you need to jump to the beginning, and I consider each jump a single instruction. So long story short, if you add them all together, the answer for the value that we get for f of n would be 8 times n plus 4, I should say, right? But it doesn't really matter. You don't need to do all these calculations in a very detailed fashion. You can say this is basically the order of n. Why? Because the plus 4 and the 8 are not going to affect the growth rate. If you want to prove that 8n plus 4 is big O of n, you can do the definition. You can just say 8n plus 4 over n, the limit when n goes to infinity, that's equal to 8. And because it's a constant, you can say 8n plus 4 is big O of n, right? Or you can even say it's theta of n. You don't need to say big O, you can even say theta. Theta means they have the same growth rate. And for those of you who are wondering why this limit is equal to 8, you can divide both numerator and denominator by n, so you get 8 plus 4n on the numerator and 1 on the denominator. When n goes to infinity, 4 over n becomes super small. It's going to become 0, so it's going to be 8 over 1. So that's why the limit is 8. And that's mathematically proving that 8n plus 4 is theta of n. In the previous slide, I showed you an example of a single for loop, and I did lots of calculations and I did lots of countings, and I did a mathematical proof to show you the time complexity is order of n. So that was a linear code snippet. But I'm not going to do this for the next two examples. I'm just going to give you a rule of thumb. I'm going to give you a good intuition or a good, yeah, I can say I can give you a good intuition, so you can just, when you look at the code, you can just feel the time complexity instead of doing many calculations and do mathematical reasoning and mathematical proofs. You can just look at the code and make a guess, and your guess is most likely correct, right? When you have a situation like this, when you have two for loops, the counters are independently increasing from 0 to n, right? In this situation, it's easy to see that time complexity is big O of n squared. Why? Because this for loop will run for n iterations. The other for loop runs for n iterations. Because we have nested for loops, the two combined will take n times n, which is n squared, right? I'm not interested in finding all the details and all the coefficient of n squared. I'm sure that if you spend some time, you can calculate, let's say time complexity is g of n, you can calculate the exact g of n, which is equal to a times n squared plus bn plus c, right? But regardless of what the value of a, b, and c are, I can say, g of n is order of n squared, right? Because as you may remember from the definitions of asymptotic notation, the coefficients don't really matter. Also, only we care about the dominant term. Between a n squared, b n, and c, c and b n are growing much slower than a n squared. So when you're calculating the asymptotic notation or big O notation, you only care about the fastest growing term. You can just get rid of the rest. That's going to be always correct if you do that. The next example, this example, is a little bit different. You have three for loops. The first for loop is completely independent of the other two, but the other two are nested. So the first one takes order of n, right? similar to the first example. And this is similar to the second example that takes order of n squared, right? So it's easy that when you add these two, because order of n squared is the fastest growing term, the result, the sum would be big O of n squared. So the lesson you can learn here is that if you have the summation of multiple terms and you want to find out the running time using asymptotic notation, only care about the fastest growing term. Don't care about all of them, right? Only pick the one that grows the fastest. In this case, I have order of n and order of n squared, but n squared grows faster, so I just drop the order of n, and I say the time complexity of this whole snippet is equal to order of n squared.